Okay, so to begin, how would you solve an equation like this? If f is a polynomial of fifth degree or higher, there's no formula. Likewise, there's no formula that will enable us to find the exact solution to a transcendental equation like cosine x minus x. We can find an approximate solution to these kinds of equations. We would use a graphing calculator. We could see that the solution is between 0.007 and 0.008, but not something more accurate. And if we zoom in, maybe we find that the solution is 0.0076. But if we need something with more accuracy than this type of graphing provides, we would use a calculator or computer algebra system to solve the equation numerically. And if we did that, we would find the actual solution is 0.07628,603. How do these devices solve these types of equations to get a number that looks like this? They would use a method called Newton's method. To explain what Newton's method is, let's start with a visual. Let's say we have a function that looks like this. This is plus y plus x. We want to know, what is this point? Where is the x-intercept? So let's take a guess. Let's pretend we start here as a guess and we say this is x1. So we go up to x1, it's up here, and we take the derivative of that value, which gives us the tangent line to this point. And this intersects with the x-axis here, and we'll call this x2. So you can see already from x1 to x2, we're getting closer to the actual value that we want. And so this is an iterative process that we keep doing. And even just after 3, you can see we're extremely close to the value that we want to get to. So now for the proof.
We want to derive our equation for Newton's method from point slope form. So we have y2 minus y1 equals m times x2 minus x1. And we're solving for x2 in this case, which is our y-intercept. And so y2, because we're solving for the x-intercept, y2 is equal to 0. And so we're plugging it 0 for y2. And then we have 0 minus y1, which is equal to f of x. And as we learned earlier in the semester, our slope is equal to f prime of x. And then we have that times x2 minus x1. So now, since we're solving for x2, we're going to isolate it. So we'll have negative f of x and divide both sides by f prime of x. So we'll have negative f of x over f prime of x equals x2 minus x1. And our last step to isolate for x2 is to add x1 to the other side. We're going to have x2 equals x1 minus f of x over f prime of x. Because our final equation is xn plus 1, so we generalize it for all numbers, equals x of n minus f of xn over f prime of xn.
To start, we will pick random x values to plug in our function to get an idea of where our x-intercept is. We want a positive and negative f of x value so we know we're crossing the x-axis.
Let's plug in 2 for x as a random guesstimate. So then we have 2 cubed minus 2 times 2 minus 5, and this gives us negative 1. Our next best thing that's above 2 is obviously 3, so we'll plug in 3 as our next number. So then we get 16 as f of 3.
Now we can see that our x-intercept will be in between these values, and it'll be a decimal close to but higher than 2. So we are ready to use Newton's formula and we will plug in 2.5 as our x1 value. So first, let's plug in 2.5 to our original function. So we have 2.5 cubed minus 2 times 2.5 minus 5. And this gives us 5.625. So now we know our f of x1 value and how close we were to 0 with 2.5. Next, we need f prime, so let's scroll back up, take the derivative of our original function, 3x squared minus 2, and now we will plug in 2.5 to this.
So we have f prime of 2.5 equals 3 times 2.5 squared minus 2.
And we get 16.75. So now we have everything we need for our second x value, so we'll do 2.5 minus 5.625 over 16.75. And we get 2.164.
So now we use 2.164, and we do this process again for x2. Now we have x2 equals 2.164. So we have x3 equals x2 minus f of x2 over the derivative of x2. So now we will plug 2.164 into our original function, which will give us 2.164 cubed times 2.164, which gives us
we get 0.80579. It's important to note that the more decimal places you use, the more accurate this formula will be. So now we can plug 2.164 into the derivative. So now we get 12.04869.
now to get x3, we have 2.164 minus 0.80579 divided by 12.04869.
All of that gives us 2.09712.
Now we have x3 equals 2.09712. So we're going to continue to plug this in. So x4 equals x3 minus f of x3 divided by f prime of x3.
So let's plug in our value of x3 to our original function and our derivative and see what we get.
This number is becoming even smaller, again, getting closer to 0. So now we have x4 equals 2.09712 minus 0.02871 divided by 11.19374.
This is equal to 2.09456. Comparing this number to what we got last time, we can see we have the same first 3 digits. And sometimes a problem will ask you to keep doing iterations till you have a certain number of same digits to your previous x value. Since you won't have a calculator when we're tested on this, it's just important that you know how the formula works and are able to use it, but you probably won't be working with decimals like this. The main takeaway is that with each iteration, we got an f of x value closer and closer to 0. That means that each repetition of Newton's method will get you closer to the real x-intercept.